Now, let's talk about physical properties of alkali metals. Let me tell you that all are metals and all are soft metals. They are so soft that they can be easily cut with a knife, and the softness increases as you go down the group. The reason is decrease in the strength of metallic bond. Lithium, being a small atom, can form stronger metallic bond. That's the reason why lithium is the hardest among them and the softest is cesium. So, as you go down the group, the softness increases, or I can say hardness decreases. Hardest among them is lithium and the softest is cesium. And then they all have a tendency, as I told you, they all have a tendency to lose electrons easily, because by just losing one electron they attain configuration similar to the nearest inert gas. So, they are never found in a free state, they always occur in their compound form. So, it is not possible to have free sodium or free lithium, it is always in the form of some chemical compound. And then also remember, they are highly active metals, they enter into chemical reactions very easily, they react almost with everything, every non-metallic species very vigorously. That is the reason why you do not find them in the free state. Let us look at their physical properties one by one. Number one is atomic and ionic radii. Atomic and ionic radii. As you go down the group, the size of the atom increases because there is increase in the number of shells. So, the order of atomic size is lithium less than sodium, less than potassium, rubidium, and then cesium. The atom having largest size among them is cesium, and the one with smallest size is lithium. Coming to see, the reason for this increase in size as you go down the group is quite obvious. It is due to increase in the number of shells on descending down the group. Now comes ionic radius. Ionic radius follows this order. Li plus is smaller than Na plus. This is also as expected. Lithium ion is the smallest one. Then you have K plus, then Rb plus, then comes Cs plus. So, the largest among them is Cs plus and the smallest is Li plus. This is the order of ionic radius. But here I would like to add one more point. There is something called as hydrodynamic radius. Hydrodynamic radius. This is the radius of these ions in aqueous solution after they get surrounded by water molecules. So, if you compare hydrodynamic radius, it is in this order. Li plus aqueous aquated lithium ion is largest among them. It has the largest size. Then comes Na plus. Then comes K plus and Rb plus and followed by Cs plus. So, if you compare the size of the ion in aqueous solution, Li plus has the largest size because it gets extensively hydrated and Cs plus has the smallest size. But in a gaseous state or in non-aqueous medium or non-polar solvent, this is the order of the ionic radius. Li plus as expected the smallest and Cs plus is the largest. But when it comes to size in aqueous solution, it is the reverted order. The reason is extensive hydration by Li plus. Now, the question arises is why Li plus gets extensively hydrated? It is because of its small size. Due to its small size, the charge density on Li plus is very high, and that is the reason why it gets extensively hydrated. Now, the consequence of this is it affects conductance. See, if you compare conductance of these ions, Li plus in aqueous solution has least conductance, and it goes on increasing as you go down the group. The reason is when Li plus moves in aqueous solution, it has to carry all the water molecules of which are surrounding it, and due to that the mobility of Li plus will be affected. It will be slower than expected. So, the conductance in aqueous solution is Li plus has least and Cs plus has the highest conductance value among these cations. So let's once again discuss about atomic and ionic radii. Atomic size as you go down the group increases due to addition of new shell. This is quite simple and as expected. And then comes ionic size. Ionic size depends upon whether you are studying ionic size in aqueous solution or non-aqueous medium. In aqueous medium, this order of size is Li plus has the largest size due to its extensive hydration, which is in turn due to its high charge density. In non-aqueous medium, the order of ionic size is as expected. Li plus has the smallest size and Cs plus has the largest size. Now, we have seen the consequence also. Due to extensive hydration, the conductance in aqueous solution is reverted. Li plus aqueous will have least conductance and Cs plus aqueous will have highest value of conductance among these ions. That's all about ionic and atomic size. So this is regarding atomic and ionic size. I hope it is clear. Now let's learn about ionization enthalpy of these elements. You know very well ionization enthalpy is the minimum amount of energy required by an atom to lose electron, the most loosely held electron, of course. Now let's see the order of ionization enthalpy. One point to be noted here is these elements have lowest value of ionization energy in their corresponding periods. If you compare ionization energies or ionization enthalpies of elements in second period, lithium has the lowest ionization enthalpy. In the third period it is sodium, in the fourth period it is potassium, then rubidium, then cesium. So these elements have lowest ionization enthalpy in their corresponding periods, lowest in their corresponding periods. You know, noble gases have highest ionization enthalpy in their corresponding periods. If you consider second period, lithium has the lowest value and neon has the highest value of ionization enthalpy. And as you go down the group, due to increase in size, ionization enthalpy decreases. So the order of the first point you need to know is they have lowest ionization enthalpies in their corresponding periods. That's the first point you need to remember. When you compare all the elements in the second period, it is the lithium which has minimum ionization enthalpy. So these elements have lowest ionization enthalpies in their corresponding periods. And then another point you need to know about ionization enthalpy of alkali metals is on descending down the group, ionization enthalpy decreases due to increase in size, i.e. decreases down the group. So the element which has highest ionization enthalpy among them is lithium and the one with least ionization enthalpy is cesium. So you can write the order of ionization enthalpy like this: lithium greater than sodium, greater than potassium, then comes rubidium, and finally cesium. So the most electropositive element, the element which can lose electron most easily, is cesium. Here I would like to add one important thing. See, their readiness to lose electrons makes them an element of choice in photoelectric cells. Potassium and cesium are used in photocells. So this is an important application exploited on the basis of their low ionization enthalpy values. Potassium and cesium are elements of choice which are used in photocells, solar cells, I can say. That's about ionization enthalpy of these elements. Look at the order once again. Lithium has the highest ionization energy and we blame the small size of lithium, and cesium has least, it is due to its large size. So this is a regular order of ionization enthalpy. One more important point which is to be remembered is they have their values are lowest in their corresponding periods. That's all about ionization enthalpy. The next property we are going to discuss is density. Densities of these elements are very low. Of course, they are all solids except francium. Francium is a liquid at room temperature, and as I told you, we are not going to compare properties with francium, as francium is radioactive. Now, densities of these elements are very low, and the element with the least density is lithium. The first comment I can make is very low densities, and then lithium is the lightest metal, not just in alkali metals, among all the elements, among all the metals in the periodic table, among all the metals in the periodic table, the metal with the least density is lithium. So, I can say the lightest metal among all the metals is lithium. Just for the sake of comparison, you need not remember this value. The density of lithium is 0.54 grams per cc. You can imagine how light it is. It is just 0.54 grams per cc. Now, let us look at the order of densities of these elements. As I told you, lithium has the least value. So, lithium is less than sodium. Sodium is greater than potassium. Potassium is less than rubidium, and then comes cesium. This is the minimum value, and this is maximum value of density. So, the heaviest metal among alkali metals is cesium, and the lightest one is lithium. There is one anomaly here. You can see density increases down the group, but there is one anomaly. Density of potassium is less than sodium. Now, why density of potassium is less than sodium? The reason large size of potassium. On going from sodium to potassium, size increases considerably. So, this will outweigh the effect of increase in the mass. That is the reason why density of potassium is less than that of sodium. Whereas, on going to the next two elements, density is constantly increasing. It is because of d orbital contractions which take place. Due to that, size does not increase much and mass increases considerably. So, density of potassium is less than sodium. This is one point we need to remember. There is another thing you are supposed to know here is the first three elements, lithium, sodium and potassium, are lighter than water, whereas rubidium and cesium are heavier than water. What I mean to say is, up to this, the elements have density less than 1 gram per cc, and beyond this it is more than 1 gram per cc. So, another point worth noting is Li, Na and K are lighter than water. The other two, rubidium and cesium, are heavier than water. That is about density of these elements. I will repeat, these elements have very low densities. The least among them and the least among all the metals is lithium. So, lithium is the lightest metal whose density is 0.54 grams per cc. Now, the order of density is like this. Lithium, there is an increase from lithium to cesium, but there is one irregularity, that is sodium is greater than potassium, and it is explained on the basis of large size of potassium, which outweighs the effect of increase in mass on going down the group. The element with minimum density is lithium, and the maximum among the elements of the group is cesium. While lithium, sodium and potassium are lighter than water, the other two elements, rubidium and cesium, are heavier than water. This is about density of alkali metals. Well, the next property we are going to discuss is melting and boiling points of alkali metals. One comment is they have low melting and boiling points. One comment is they have low melting and boiling points. The reason is their strength of metallic bond. See, these elements have only one valence electron, so the strength of metallic bond is very weak. Because of weak metallic bond, their interparticle attractions are weak and they melt at a very low temperature. But the order of melting point is like this: lithium greater than sodium, then potassium, then you have rubidium, and finally cesium. You can see melting point is decreasing on descending down the group. The reason is the decrease in the strength of metallic bond. You know, metallic bond strength depends on two factors. Strength of metallic bond depends on two factors. One is number of valence electrons, and another factor is atomic size. You know, as the number of valence electrons increase, strength of metallic bond increases, and as the size increases, strength of metallic bond decreases. Strength of metallic bond decreases with increase in size. So, as you go from lithium to cesium, number of valence electrons remains same. They all have one valence electron in their atoms, but the size is regularly increasing. Cesium has the largest size. Because of large size of cesium, the metallic bond strength in cesium is low, and that is responsible for its low melting point. So, this is a regular order of decrease in melting point. This is minimum. And it is very close to 30 degrees Celsius. The value, you need not remember the value, just to have an idea that if you put a piece of cesium on your palm, it will melt due to your body heat, as your body temperature will be around 37 degrees Celsius. So, this shows very low melting point of cesium. Same order is followed for boiling point also. Boiling point also follows the same order. The element with highest melting and boiling point is lithium, and the one with least melting and boiling point is cesium. And we blame strength of metallic bond. Down the group, there is a decrease in the strength of metallic bond. Therefore, there is a decrease in both melting point as well as boiling point of these elements. Order is very simple. It is as expected. A regular order, no anomaly here. That's all about melting and boiling points. The next property we are going to discuss is standard oxidation potential of these elements. See, standard oxidation potential is a measure of ability of an element to undergo oxidation. If you look at alkali metal, this is a general representation I am showing for an alkali metal M, which is a solid. When it loses electron in aqueous solution, it becomes M plus aqueous. It is losing electron. Now, you can call this reaction as oxidation. If you look at it in this direction, you call it oxidation. Loss of electron is called as oxidation. So, alkali metals, we told in the beginning also, alkali metals have a tendency to lose electron, and they tend to lose only one electron because they have only one valence electron. They lose this electron very easily. The reason is, the moment they lose electron, they will attain noble gas configuration. Apart from that, they have very low ionization energy because of large size. So, their tendency to lose electron is very high. The moment they lose electron, they lose one shell and the size considerably shrinks. They have very small size of their cations and they get extensively hydrated. That becomes a driving force for them to lose electrons. The loss of electron is, the energy required for the loss of electron can be easily compensated by enormous amount of hydration energy which is accompanied in this process. So, alkali metals have a great tendency to lose electron, and this tendency we expect it to increase down the group because there is a decrease in ionization energy. Now, the measure of ability of an alkali metal or any metal to lose electron is called its oxidation potential. Now, the order of oxidation potential E naught, we are taking it in SOP. Matlab, SOP represents standard oxidation potential. The element with highest SOP, standard oxidation potential, is lithium. Then comes sodium, and then sodium is less than potassium, potassium is less than rubidium, and there is a marginal difference here. There is a marginal difference from potassium to cesium, there is a marginal difference. This is the order. So, you can say generalized way it is supposed to increase down the group, but there is an anomaly. The most important question here is what makes lithium a most powerful reducing agent. I mean, lithium has a great tendency to lose electron as per this order. See, any species which loses electron will behave as a reducing agent, because loss of electron is called as oxidation, gain of electron is called as reduction. So, any species which is losing electron will be responsible for some other species picking up that electron and getting reduced. So, if an element has very high oxidation potential, it will have a great tendency to lose electron, and it will therefore behave as a very good or very powerful reducing agent. So, these values, this order represents the ability of these elements to lose electrons, and the ability is highest in case of lithium. Lithium has a great tendency to lose electron. Let us try to find out why lithium has greatest tendency to lose electron with the help of these reactions. The various processes which are accompanied in this overall change are like this. Lithium, which is a solid, will first transform into gas. This will consume energy which is called as sublimation energy, which is represented by S. Then Li gas becomes Li plus gas. This involves loss of electron, and the energy change involved in this process is taken as ionization enthalpy. Now, it becomes Li gas now becomes Li aqueous. This is the energy change in this process is taken as hydration energy. While sublimation energy is endothermic, this change is also endothermic, whereas this change is exothermic. If you compare on the basis of sublimation energy or ionization energy, the advantage will be for cesium. But when it comes to hydration energy, lithium has a very, very high value of hydration energy. It will outweigh the effect of sublimation energy and ionization energy. That makes lithium a very powerful reducing agent, or that makes lithium to have highest oxidation potential value. So, remember that this is the reason why lithium has highest standard oxidation potential, enormous amount of hydration energy. Now, why its hydration energy is very high, it is again explained on the basis of its very, very small size. Due to its small size, it gets extensively hydrated and produces enormous amount of energy, which is called as hydration energy. So, this is the order of standard oxidation potentials. See, on the basis of this order, we can compare their ability as a reducing agent in aqueous solutions. The one having highest standard oxidation potential is taken as the most powerful reducing agent. So, which is the most powerful reducing agent among alkali metals? The answer is lithium. This argument holds good in aqueous solution. The standard oxidation potential values are assigned on the basis of reaction taking place in aqueous solution only. So, hydration energy has to be considered, and it is the hydration energy which makes lithium the most powerful reducing agent among all the elements in the periodic table. If you see the electrochemical series, at the top you will find lithium, and at the bottom you find fluorine, indicating that fluorine has a great tendency to gain electron and lithium has a greatest tendency to lose electron. So, you can say lithium will be the most powerful reducing agent and fluorine is the most powerful oxidizing agent. That completes this factor, standard oxidation potential. Just go through the order once again. Lithium has the highest, and this is the minimum value. This is maximum. The least powerful is sodium, and the most powerful is lithium. The next property we are going to discuss about alkali metals is their ability to produce characteristic color when exposed to Bunsen flame. When the alkali metal salt is exposed to Bunsen flame, it changes the color of the flame and gives a characteristic color. So, this is due to electronic excitation which takes place during its exposure to the Bunsen flame, and then the electrons will come back to the ground state. When they come back to the ground state, they produce color, characteristic color, and this is the list. Number 1 in the list is lithium. The color produced by lithium is crimson red. Sodium produces golden yellow color. Potassium produces lilac. Rubidium, ruby red, and cesium produces blue coloration. When this alkali metal salt, when any alkali metal salt is exposed to Bunsen flame, it produces color which is characteristic of the alkali metal. If the metal is sodium, the color produced by the Bunsen flame will be golden yellow. This can be exploited in their characterization. If you have an unknown alkali metal compound, just take a small pinch of it and expose it to Bunsen flame, and from the color you can say whether it is potassium, sodium, lithium, rubidium or cesium. So, this behavior is useful in characterization of alkali metals. You can identify the alkali metal salt on the basis of that. If you are not sure whether a particular compound is a sodium compound or not, take a pinch of it and expose it to the Bunsen flame and observe the color of the flame. If it gives golden yellow color, then you are sure that it is sodium compound. This is flame coloration. I told you this is because of electronic excitation which absorbs the heat from the flame, and when the electrons return to their ground state, they emit energy in the form of visible radiation of characteristic wavelength. If it is lithium, you get crimson red color, sodium gives golden yellow color, potassium lilac, rubidium gives ruby red, and cesium gives blue color to the Bunsen flame. The reaction is used, this property is used for the characterization of alkali metals.